Retakh, sorry, who is going to speak about non-commutative cross-ratio and super Schwarz derivative.
Okay. So thank you very much for the invitation. It's a pity that I cannot be there. And my talk is related to a program which is unofficially called non-commutative theory of everything. And today I would like just to discuss two classical invariants, Crossratio and Schwarz derivative. And when you are doing this in the non-commutative case, you have some new effects, like, for example, for Schwarz derivative gives a strange invariant related to so-called, for super algebras, strange invariant. It's called queer trace, but we will come to this. And I will start with Crossratio. So I have a division ring, and I will try to imitate the definition of the classical Crossratio in homogeneous coordinates. Actually, everyone who attended Gelfand seminar knows the definition that was used there, and the definition was that so you have a plane and you want to introduce a coordinate system. So for this you need two straight lines intersecting in a point, say O, and then to introduce coordinate system you need another line which is sort of play the role y equals x, and which allows you to connect O axis with the OY. And then if you will draw the fourth straight line with the equation y equals kx, then k is exactly the Crossratio. So in terms of equations, and I will do this in the non-commutative case, so I have actually just a plane R2, which is, but I will consider multiplication from the right. And so I have actually four vectors, so A, B, C, D. Now, in commutative case, so the equation is C equals A plus B, and then D can be presented as KA plus B, and K is Crossratio. So in the non-commutative case, what we have actually four vectors, which you can see here, X, Y, and so on. And then we define the Crossratio by the equation that, like, so T is equal to X alpha plus Y beta, and Z is equal by the equation that you can see. So these coefficients are from our division ring. And in the commutative case, you can express Crossratio by using Plücker coordinates. And in the non-commutative case, you can express K using so-called quasi-Plücker coordinates, which were introduced by Gelfand and me, well, years ago. Okay, so I will just formulate the definition. So if I have this but I will do this only for 2 by n case. I don't need more general stuff. So if I have just 2 by 2 matrix, then I can define so-called 4 quasi-determinant determinants. Okay, you see the formula, and this is sort of good if you work in some categories, and A is a morphism because everything is composable. So you can actually define actually 4 such expressions. Okay, and then to consider the ratio of such, if you have of such quasi-determinants, if you have 2 by n matrix, it's written here. And what is interesting that if you define this ratio, then so first of all, so this is one column is common for the nominator and the denominator, and you have to start with some actually elements, and you must start with elements on the same level. So this is A1I, A1J, or A2I, A2J. Okay, so it's easy to see that in the commutative case, you have basically the ratio of 2 Blücher coordinates of this matrix to the Blücher coordinates of that matrix. And okay, I agree that this definition may look ugly, but the justification is the following result. So this is our notation for quasi-Blücher coordinates of A. Again, then here is expression as a ratio of 2 Blücher coordinates. And the properties of these Blücher coordinates are the following. First of all, they are invariant. So if you take invertible 2 by 2 matrix over this division ring, and then after multiplication of A by G, so this you have the same expression. So that's invariant. And not surprising if you consider this commutative version. Now there is.
Excuse me.
Yes.
So it's just a product, just to clarify, there is no summation. Although I and I appear twice, say, there's no summation there.
No summation, no. What do you mean summation? This is...
Well, you have expression with up and low indices.
Yes.
And...
No. This means actually that here you have, so that's, you have columns number I and number K, and then you have also column number J and K. This is just, so this, there's no summations here. Okay, let me maybe show you this again, that this is just, so what you have in the commutative case. Okay, so this is GL2 invariant. Now there is actually strange non-commutative skew symmetry, and which is actually says that the product, so I will omit this A capital, so the product of these 3 quasi-Blücher coordinates is equal to -1. Well, in the commutative case, it follows that from this that Bij is equal to the minus Bji. And you can rewrite this formula if you wish. And there is what's called non-commutative Blücher identity, which is here. And if you can just if you can write the commutative analog, you will have exactly the classical Blücher identity. Now this actually, and now this formula works, for example, relatively recently, Arkady Bernstein and I, we constructed a non-commutative version of this Ptolemy identity by using actually this approach. All right, but this is so I introduced this. Now, there are additional properties of this quasi-Plücker coordinates. What's important, that Qijk is inverse to the Qjik, and we will use this. And now I can produce the formula for this quasi-Plücker, for this cross-ratio. And so I have 4 columns, or 4 vectors, and here is the formula for, for this non-commutative cross-ratio. And if you specialize this in the commutative case, you will have this canonical cross-ratio. Okay, now let me just maybe list some properties of the cross-ratio. But first, this is justification is their behavior under projective transformations. So I have 4 vectors x, y, z, t. I have just GL2 matrix, and I have elements lambda I, which acts on my vectors from the right. So, and then, first of all, the behavior of cross-ratio is like this. So in the commutative case, you have the same cross-ratio. In the non-commutative case, you have the quality up to a conjugation, and this is actually an effect of this non-commutative approach. Everything is sort of equal, but up to a conjugation. So let me consider then just the non-commutative torus, which is like this. And then I can define the non-commutative version, the action of GL2 times this torus on P4. And there's this theorem that when I can go from 1 4 tuple to another 4 tuple, and it says that I can go from x, y, z, t to x prime, y prime, and so on, by using this GL2R times this torus, if and only if they are cross-ratio can coincide up to a conjugation. All right. Now properties. Well, it follows exactly from quasi-Plücker relations. So this is properties. This is, and of course, we know that in the commutative case, if we permute x, y, z, t, then we have 24 cross ratios, and we know relations between them. And now in the non-commutative case, you have more or less the same relation, but again, the conjugation appears in almost all these formulas. Let me recall that QTZX is inverse to QZTX. So just this one. Okay, and here are more formulas here that you can see, but I will not give you all possible all possible, or all 24 formulas. So this is, so the formulas is here. Also, there are some relations. For example, if you have 5 vectors, how those cross ratios behave, and so on. And now then, cross ratios for quaternions were actually used by Igor Frankel and his student Libin, actually in applications to physics, and actually their properties of cross ratios for quaternions follows from this more general stuff that I discussed. Okay, now let me talk about applications, maybe. And this is a joint work with Vladimir Rutgers and Georgy Sharygin. And I will start with the so-called pentagramma mirificum by Gauss. So Gauss observed that when you have a pentagramma on the unit sphere in R3, and which is defined by successively orthogonal great circles, and the length of the inner side of these circles is alpha I. And if you introduce variables y sub I as a 10 square of alpha I, then you have actually sort of 5 relations like this. And also Gauss noticed that equations for I equals 1, 2, 3, they define 4 other relations. Okay, now I learned about this pentagramma relations from actually a review by Sophie Mourier-Guinaud, if I pronounce the name correctly. And so actually, she noticed that actually that if you just write an expressions for yi equals some, using some Plücker coordinates, using actual coordinates of 5 points, then after remaining this, you have the following interesting pentagon recurrence relations, which are written here. And of course, this is one of the favorite examples in cluster algebras. And so this is, so xi can be written as Laurent polynomials in x1 and x2. But basically what you have here, you have periodicity. For example, x6 will be equals to x1, x7 will be equals to x2, and so on. Okay, and then we tried actually to understand the situation in the non-commutative case. And in the non-commutative case, if you, replace this, the expression that I just wrote by using cross ratios, and so the formulas are here. So you have like 5 vectors and 5 cross ratios. Then you are getting the following relations. So again, that you have like x1 times x3 equals 1 plus x2, but x3 must be conjugated. And the same in other cases, but also note please that you have different order when you start with the even x or with an odd x, because here you have first x and then x3, and for x equals 2, you have first x4 and x2. Okay, now if you can introduce on all this situation actually just an anti-involution, which is described here. And then you get that x6 is equals to x1, but bar of x1, and x7 is equal to bar of x2. So here you have actually the 5 anti-periodicity. So you have this periodicity up to an anti-involution, which is written here. Okay, maybe I will skip these two more applications, and this is there is a non-commutative version of a leapfrog map. Leapfrog map, as it was an example of an integrable map introduced by Gehman, Shapiro, Tabachnikov, and Weinstein. And also non-commutative cross ratios were considered by experts actually in control theory. I believe Zelikin was the first. And again, let me just maybe skip this stuff, but the operator cross ratio introduced by Zelikin actually coincide with a version of the cross ratio, of the non-commutative cross ratio that we discussed before. Great. Now, since we started to talk about cross ratio, it would be interesting to know when to discuss problems, actually elementary problems, when you have triple ratios. And so let me discuss actually very old stuff, and this is theorems of Menelaus and Cheva. So then suppose R again is a non-commutative division ring, consider it as R2 is a right vector space. Suppose you have just a triangle ABC. Then, as actually we all did in our maybe middle school, you consider points D, E, F. So D on the side AB, E on the side BC, F on the side AC. And the question is when those points belong to a straight line. And this is sort of course, Menelaus theorem. And the answer is that this point belongs to a straight line if and only if you have the following product. So he must be coordinates A sub I and F sub I am midget I. So you have this product, of course, that you can, of course, get the classical theorem in the commutative case. But again, just I would like to draw your attention that as always in all these theories, negative powers, they are just non-negative. So this is, you have powers, so -1, +1, -1, +1, and it's always the case in all similar problems. Okay, and then the dually you can obtain the Cheva theorem, which says that again, the question is when those three lines intersect in one point, and again, the answer is actually similar, except that you have -1. And so why we were interested in this stuff, because there's an application of this classical theorems to integrable system that were discussed by Schiff and Konopetchenko. Okay, now I have a question then. Do we have a 5 minutes break, or I just can continue?
Continue.
Well, okay, so I will continue for like approximately 25 more minutes. Okay. Okay, now let me talk about non-commutative Schwarzians, and basically I will start with the old paper, with the joint paper with Schander, who was actually a big expert on superalgebras. And so let me formulate our approach to this Schwarzian derivatives. And so suppose again you have an algebra, non-commutative or otherwise, you have a subalgebra R0 and another subalgebra C, and which is sort of a constant. Then on R2, which here it's more convenient for me to write as a row vectors, you have actually two actions. You can multiply from the left by some invertible elements from R0, and of course, and then you can multiply by 2x2 matrices from the right. And we are looking for invariant of this action. Now, in classical case, usually people do not do this, and because they would consider the ratio of when F1 to F2, say called phi, then you do not need to consider the left action. And then you just applications of this 2x2 matrices. This is like a Möbius transformation. And then you have a classical Schwarz derivative for phi. Okay, now let me try to discuss a sort of a non-commutative version. And basically also trying, but we try to imitate actually classical construction actually of Schwarz invariant by using actually differential equations. Okay, and so let me suppose that D is a derivation. So this satisfies Leibniz rule. And then I can define Wronski matrix, which is written like this. Well, F prime, I will write F prime instead of DF, so it must be small f here. Okay, and just okay, let me down. Okay, and then I will construct, actually, in this case, I can construct just the differential equations of the second order, which you can write here. And all I need just to define, and such that F1 and F2 are solutions. And actually, all I need is to define A and B, coefficients. And so I can do this if this Wronskian is invertible, but with the extra condition, I can actually, those actually A and B are actually also quasi-Plücker coordinates, but they're quasi-Plücker, so-called right quasi-Plücker coordinates, because the matrix here is 3x2 matrix. T means transpose here. And even I will write you the formula, and again, but since this is right quasi-Pluker coordinates. Now this is the inverse goes not to this fraction goes not to the left, but to the right. So those are formulas. Now, suppose C is an algebra of constant, so that's the derivative of this.
May I ask a question?
Yes, please.
So is it like Kramer's formulas for determining the coefficients?
Yes,
Non-commutative Kramer's formula.
Yes, exactly. Yes, it was done in this way. Yes, exactly.
Thank you.
Okay, and so now suppose that C is an algebra of constants, then and then GL2 of C. Just so A and B are invariants after GL2 of C. And after we write this constant. And then what we are trying to do is actually to consider this equation. And in the classical theory, people try to kill A. And if you kill A, then by just acting on F1 and F2, then you will have just a solution for B. And this B will actually give you this classical Schwarz derivative. Now, sometimes you can do this in the non-commutative case as well. And again, this was done in this paper by, this was actually done in paper with Schander, then repeated in our paper with Rubtsov and Sharygin. And so again, this transformation change A and B. And if you are lucky and you may try H that satisfies this condition. And but in this case, so this condition, then you can kill A completely, and you have the following formula for B. And now again, in the commutative case, of course, you can forget about this conjugation, and so you have this just a classical Schwarz derivative, which is actually written here. Just forget this. But actually, if you now, but if you are acting on your F1 and F2 by this subalgebra R0, by invertible element from R0, you cannot kill A completely. And let me just give you an example when you cannot do this. So suppose C will be just a finite dimensional Grassmann algebra over R. So free superalgebra. Now R will be just actually functions, the ring of functions with the value in C. Now R, and suppose that you have a super case that R is a direct sum of its even and odd part. And by multiplication of F1 and F2 by invertible even elements, you can kill only the even part of A. And the remaining odd parts, and the formula is here, it was obtained with in the paper with Schander. This is actually this R0 times GL2 of C invariant. Now, the formula, what is written here, so you take the Vronsky matrix, you take what's called queer exponential trace of W, and you take the derivative. Let me recall what is queer exponential trace. So queer trace actually in, for people doing superalgebra, it's called, so if you have a matrix, then the queer trace is just the sum of the diagonal of the odd parts of these diagonal elements. And then you may consider then you may consider this queer trace of this, of the powers of this matrix, well, divided on 1 over I, and it's called the queer exponential trace. Now, I did not invent this notion and this notation, so, but anyway, so the formula looks like this. And so this is actually, again, this is some sort of a Schwarz-like invariant, but all I can say right now is just to give you this formula. Okay, now maybe just a few words about integrables, Schwarzians and integrable systems. And again, this is from joint work with Rutgers and Sharigan. So suppose you have a division ring equipped with a derivation, and then you have two such equations, area-type equations. Okay, and then under some certain condition, so when H is actually, say, the right ratio of F and G, you can produce this equation, which is actually non-commutative, again, analog of the Schwarzian, this type. And so what you have here on the left, this is actually also a version of a non-commutative Schwarzian. Now, and if you add just assume that in R there are two derivations. One is, the derivation that we introduced before. Another one is derivations over T, well, symbolically, and those two derivations commute. Then you may consider such an equation. And this equation is actually in the commutative case, it is known that this is that by using Schwarzian derivatives, then you can just get this version of this KdV equation, and by introducing this two commuting derivative in the non-commutative case, you may try to write actually a non-commutative version of KdV. Okay, now, okay, so this is, and I first actually just got a non-commutative version of this KdV, which is actually different from this, and it was in our paper by Ettinghoff and Gelfand, but I believe it's 97. And all I want to say that this non-commutative equation has actually an interesting geometric specialization, and it was just a paper by Befa, which is called Moving Frames, Geometric Poisson Brackets, and the KdV Schwarzian Evolution of Pure Spinors. And this basically, they had, so that she had actually an equation of this type. Okay. All right, now I understand that. So just, I don't have that much time, but again, that, just it was, it's very well known that Schwarz derivative is actually a sort of infinitesimal version of the cross ratio. So let me just very briefly attend this. So again, I have R2, so this is direct sum. So suppose I have a smooth one parameter family of elements, and suppose that I have actually this type of cross ratio, which depends on four parameters. Okay, now then by introducing this ratio, well, in this case, this one, okay. And so when I introduce this ratio, I can consider the derivations, and this is basically, again, non-commutative analog of the Schwarz derivative. And again, I will not write you this infinitesimal, let's go, just going to just through limits and so on. All I want, and maybe that's in the end, I want just to state the formula, which it's here. Oops. So this Schwarz derivatives is actually, when you are writing actually some sort of a Taylor series, you have an expression like this. So here are terms of the high order, but here you can see exactly this Schwarz derivative. And then again, in the commutative case, such formula appears in a paper by Agrachov also. And actually, again, it was about contour theory. All right, and so maybe I will stop here then. So thank you for your attention.
So I have a question about
yes.
The quasi-Placer relation in the non-commutative algebra. Okay, can we how we can use it for the super commutative algebra? If the